This section will focus on Snort NIDS, a network intrusion detection system which is freely available and functions as a packet sniffer, a packet logger, as well as an NIDS engine. Let's open the shell and launch our notes, and then we'll proceed to download Snort from snort.org. And we'll just wait for this to finish loading the full buffer and create a section named Snort NIDS. So again, Snort NIDS features an NIDS or network intrusion detection system. And it is able to sniff traffic directed to the Snort hosts or to other hosts, communications between other hosts, if port monitoring or span or some similar feature is enabled on your switches to allow Snort or the system running Snort to see the traffic or the communicate between other systems on the network. And it is able to decipher from that traffic or those traffic streams whether or not the communique is considered potentially hazardous or lethal or against your security policy, because Snort includes a database or a signature database with patterns of various types of exploits, various types of vulnerabilities that it searches for. So it matches the traffic that it is processing in real time against a signature database to make a determination. That's when you operate Snort in NIDS mode. It also operates as simply a packet sniffer. Similar to TCP dump or Snoop within Solaris, we can use Snort to sniff traffic destined to any of our network interfaces. And again, if the network interface is connected to a switch port which has port mirroring or span or a similar feature enabled, Snort will be able to intercept that communique and process it, make sense of it, and if need be, will be able to export that information into TCP dump format for further analysis using tools such as Wireshark and others. So it is a packet sniffer, and it is also a packet logger. It logs to TCP dump format, or logs using TCP dump format, which means any TCP dump compliant application such as Wireshark will be able to process the TCP dump binary file produced by Snort. So there are three modes. We'll begin with the basic mode, which is packet sniffer, then graduate to packet logger, and then end our discussion by setting up and exploring Snort as an NIDS. So let's set up some tasks, including one to download and install Snort, the latest version. We'll navigate to snort.org, to the download section. Let's pull a browser up. And this should be up momentarily. We'll navigate to snort.org and search for the download link, which is on the left-hand side, Get Snort. And here's the latest version. And we can download it, place it on our system. It includes a checksum file as well as a signature file, which allows you to confirm the GPG signature that was used to sign this particular release of Snort using GPG, or any PGP compliant application. You'll need to download the public signature that was used to sign this release of Snort to confirm it. We'll do that as well. So let's download the current version. This will pop up and ask us if we'd like to save it somewhere on the disk, or we could copy the URL and use wget directly from the shell, which is my preference. So let's navigate into temp. We'll make a directory labeling it Snort, and then we'll wget the URL. This will pull Snort to the current directory. It should be down in no time. We should also get the MD5 as well as signature files, We'll copy the link location for each. Once this is complete, we'll wget it. And we can use a little command sequencing here to run multiple commands to pull both the MD5 checksum and the signature. Let's copy the link location, and this is command chaining, the more apt term, the more correct term, which is of course command sequencing, and in our case we're using a little logic, and logic, so if the first is successful, then pull the second. So now we have all three files. The primary tar.gz image, which contains Snort in a non-compiled version. This represents Snort in its uncompiled version or uncompiled form, which means we'll need to have a compiler installed in order to compile it to produce a binary that's compatible with this hardware. The MD5 checksum, which should match the MD5 sum executed against the tar.gz image, and the official GPG signature. To check the MD5 sum, just run MD5 sum against the binary that's downloaded. So snort.org, and we'll confirm MD5 sum by simply executing MD5 sum against the name of the Snort binary, and then comparing that to the output from the file that we downloaded. So we'll note compare to .md5. Let's do that quickly. We'll execute MD5 sum, and since it's a small file, it returns the signature very quickly. Begins with C4, terminates with CB. Let's cat the contents of Snort tar.gz MD5, and we see also it begins with C4, terminates with CB. If one bit is different in the Snort version tar.gz image, then its MD5 sum will change and will not reflect the MD5 file that we've downloaded. So far the MD5 has checked out, telling us that the file has not been tampered with during transmission. The next step is to confirm the signature, the GPG signature. In order to confirm the GPG signature, we need to download the signature used to sign the package. We see here that the current release was signed with this PGP key. So we must import the key. We can copy and then paste this into our GPG input. So let's just note as our next step, step C, import GPG key used to sign Snort. And let's just indicate the current release of Snort, followed by a GPG verify to confirm that what we've downloaded is indeed the package that was created, or the tar.gz image that was created by the folks who put together Snort. So we'll verify momentarily. Let's import the key, which is still in memory. If we GPG list keys as a user Linux CBT, we'll see that we have keys that we created during our testing. However, GPG import will allow us to paste on the command line the full key that we've downloaded from the internet, that we've copied from the internet. Control D will complete the process, and if you read the output, you'll see how many keys were processed, the trust level assigned to the key, so on and so forth. So we've imported the key with the following key ID, and a re-execution of GPG list keys will reveal that the Snort key, which expires in 2008 on 8/20, is on our public keyring and can be used to confirm files that have been signed by the Snort team, release files that is, including the snort.tar.gz file. Now, since the signature file has the same base name as the file to be checked, all we need to specify is the name of the signature file. But if the file names are different, then you'll need to specify both. So we'll verify the signature file, but optionally we could indicate the name of the file to compare the signature against. But again, since the signature file has the same base name, we don't need to specify the file to test. Let's try to verify. And we see that the signature was made on a certain date at a certain time, and it's a good signature from the Snort release team. we haven't assigned a trust, we haven't signed this public key, so the trust level is marginal to none. But that's besides the point. The point remains that the signature is good. If there were a problem confirming the signature to the tar.gz image, then GPG would return an error. So the signature is good, we can trust it, and at this point we can extract the contents of Snort and begin the compilation process. Now, compilation does require that we have GCC and make. We should just note, but we'll do so during the compilation. So we verified, and step D will be, or step E that is, will be to configure Snort. Now, one other note, we should ensure that we have libpcre installed. Let's rpm query all grep I libpcre. This is the development library that's used to provide Snort with access to Perl-compatible regular expressions. It's usually represented as libpcre or as simply pcre devel, and it may or may not be installed. If it's not installed, we want to install it. We see pcre is installed, but not the development package. And if we search for it using yum as root, of course, let's sun. So perhaps we'll just take the time to list some of the requirements. Requirements include GCC, this is the C compiler, make, which makes the binaries, libpcre, which is usually implemented as pcre-devel, and let's just check our repository located at 192.168.75 100 rh5 in the yum directory. We should see a list of packages, and we'll search for pcre once the list has been displayed in full. And momentarily we'll control F and search for pcre. So we see the main package and also the development package. This is what we'd like to have installed. Depending on the distro, this is Red Hat, so it's represented as pcre-devel. Other distros may call it libpcre, but they're both the same software. So let's yum install pcre-devel. This will pull the latest version. We'll query the yum repository and ask us whether or not this is what we'd like to have installed. We'll confirm, of course, and momentarily the development package will be installed. Again, pcre-devel provides Snort's access to Perl-compatible regular expressions. So provides access to Perl-compatible regular expressions. This is a crucial library that Snort relies upon, as Snort parses data that's read from its network interface or interfaces and compares it to signatures using the Perl-compatible regular expression engine. Now there is one other requirement if you intend to run Snort as an NIDS and log to a database such as MySQL, or in particular MySQL. That is the MySQL development package. So we'll need to ensure that we install MySQL development. This provides access to MySQL so that Snort can log to the MySQL server. So with that said, let's proceed with our process. We've installed pcre-devel. We should also install, since we're here, the MySQL development, otherwise compilation will fail. We'll control F, search for MySQL-devel, and we see that it's available as MySQL-devel followed by version, so we'll yum install MySQL-devel. Might as well get all of these packages out of the way, and it should prompt us momentarily. And this is how it is installed. And then that leads us to step E, once we've taken care of the prerequisites, which is to extract and install, which means really to compile Snort NIDS, which yields the binary that does the work. Let's proceed with MySQL-devel. And now that that is in place, we can move forward. So we've confirmed the signatures, or the signature and MD5 sum, which functions as a signature. Let's tar x zvf. And by the way, at this stage, we can drop privileges to non-root status and then extract compile. And then, when ready to populate the user directories, we will then revert to root access, as root access will be required. So we'll tar x zvf. This will create a subdirectory structure with the prefix snort dash followed by the version. And these sub-steps are important. So tar x zvf, the name of the package. This creates top-level directory with all of the source files necessary to compile Snort. And it's fully extracted, so now we may navigate into that directory, and as you download subsequent versions of Snort, you can extract them beneath the path that we've created thus far. Beneath the user's home directory, temp, Snort, subsequent versions such as 2803, 2804 will be created in their respective directories. So from this directory we'll run configure. Configure supports myriad options. Execute configure with help, and you'll see those many options which provide Snort with the ability to talk to different databases, support different libraries. Here are some databases such as ODBC, MySQL, PostgreSQL, PGSQL, even Oracle. The ability to talk to different libraries, different engines, enable IPv6 support, which may or may not be important in your environment, and other items. There's some important items that we'd like to enable, so let's set up our configure script. This is by no means mandatory, but it works for many configurations. It's a simple configure with MySQL support, which searches the system for the MySQL development traces or libraries to be able to connect to MySQL. And we'll enable dynamic plugin support so that we can add additional functionality to Snort when necessary. Snort is modular like Apache and other programs. This will take care of our needs, but again, there are many other options. Just scroll through the configure dump to get a sense. When you run it with help, you'll see the options that are supported. You can change where the system binaries versus user binaries are stored, the live directories, where to find libraries, the data root directory, from the default varlog snort to something else, documentation. You can configure most aspects of the compilation process by running configure with the appropriate options. If you're running, for example, a 64-bit version of Linux and you'd like to compile Snort with, or even of Unix, compile Snort with 64-bit GCC support. Supposing you have the C compiler which runs on a 64-bit platform, you'll need to enable 64-bit GCC, and many other options are supported. So with that said, let's move towards the bottom. We're not going to go through all of the options. And we can launch the configure process as a non-root user. This will search the system to ensure that the prerequisites are met, which include GCC as well as make, libpcre, MySQL devel. So let's just note checks for prerequisites. Including MySQL devel, libpcre, GCC, and make, among other things, which will exist or be available on your system. Now, this process is prone to errors. It's not an error-free process. If something is missing, like in this case, we thought we had libpcap installed. It isn't. We need to have this installed. So let's list it as another item which eluded us momentarily, and that is libpcap. This package is usually installed, and this provides the TCP dump packet capture library, which Snort so heavily depends upon. So in our yum repository, we'll search for pcap, and we'll see that libpcap is implemented as the following packages, which we thought we had installed on our system. we can of course RPM query all grep case insensitive pcap to see if there are any traces of pcap, and we see the main package but no development package. So with that said, we'll SU back in and then install using yum the libpcap develop package. But the good news is most configure processes will behave exactly as we've seen here, and that is to warn you when packages are missing that are critical to the success of the application. So the Snort configure process cannot move forward without libpcap, because Snort's basic functionality, whether in an IDS, packet sniffing, or packet logging modes, relies upon libpcap to intercept traffic, not necessarily to parse the traffic, but to intercept it, to place your interface into a mode in which it's able to extract the packets off the wire. So now we have it installed. Let's try to rerun the configure process after having dropped privileges to the user Linux CBT. And this will run through the process again, and it's searching for all sorts of dependencies: grep, egrep, LD, strings support. It's searching for, or it's searched for a C processor, C++ that is, processor. And along the way you'll see the dependencies either fulfilled with yeses or unfulfilled with no's. And not all no's are bad. Not all items are required. Some things are helpful, some things are optional, others are mandatory. And this is moving forward. It found the libpcap this time in order to again pick up the packets off the wire. Now when you get this far where you see the config status files being created, the various make files for the different binaries that are to be produced, you know that you've met the dependencies, you've met the prerequisites, and momentarily we'll be able to echo the make process. So far so good. We can now execute make. Now make is available for non-privileged users, so let's move forward and execute it. This will create the Snort binaries that will run on this x86 32-bit based system. You can also copy these binaries to another similarly configured system. So if you have another Red Hat system with the same prerequisites in place, which of course includes a C compiler make, libpcre, MySQL devel, libpcap, in particular these three, GCC and make are used to create the binaries, whereas libpcre, MySQL devel, and libpcap are used at runtime for their various purposes. libpcre for parsing the traffic that's intercepted by libpcap off the wire after having placed the interface into promiscuous mode, and MySQL devel for logging the parsed traffic, at least the alerts, into a MySQL database structure, table structure that we'll create once we look at setting up Snort in IDS mode. Once we have Snort installed, we will look at it initially in packet sniffing and packet logging modes. Let's take a look at the process to see where we are, and so far so good. The make process seems to have executed. It has returned an exit status of 0. At this stage we need to SU in and execute make install. So E3 is to execute make. This creates binaries. E4 is to SU as root and execute make install. Make install places the binaries in user local accessible location for all users to be able to access Snort. Let's execute make install, and you'll see traces of where Snort's placed on your system. User local lib as well as user local bin. And this should be available momentarily. There are quite a few items to populate on the system, but once it's up, we'll be able to run it. Let's just stretch this out to make some space. And just like with TCP dump and Wireshark, Snort has direct access to your network interfaces. So it's able to sniff traffic on any of the interfaces you have configured. And ideally you should execute or operate Snort on a system that's multi-homed, one with multiple interfaces, using or reserving one interface for management and the other or more for network sniffing, so that you always have a way to get into the system. Documentation is copied to user local share doc Snort. And we should be going momentarily with packet sniffing and packet logging. Right, so now if we execute which Snort, we see that it's in user local bin. We specified user local because Snort's copied to user local lib as well as bin as well as share doc Snort, so it's all throughout user local, but it is in root's path, which means we may execute it. Let's create a subsection, usage, and we'll begin by discussing Snort as a packet sniffer. So usage as packet sniffer, and then we'll have a separate section for usage as a packet logger. As a packet sniffer, you'll execute Snort with verbose mode turned on, and you'll also indicate the interface unless your default interface is the lone interface. But it's always a good idea to indicate the interface even if there's only one interface. So -I indicates the interface just like with TCP dump, and that's ETH0, which we can confirm using ifconfig. We'll clear screen, execute ifconfig, and since we've SU'd in, we need to execute the full path. We see that ETH0 is our primary interface. ETH0:1 is an alias interface, which is a spillover from the section where we looked at IP configuration. So ETH0 will be the interface that Snort will sniff on. If you execute Snort with no options, towards the top it tells you the version. If you scroll all the way up to the top past the myriad options, that indeed the current version that we're running is 2802. It's usage, which is basically executed as Snort, any number of options, followed by filter options. Filter options refer to Berkeley packet filter syntax, the ability to focus in on specific protocols, packet types, port numbers, etc. And you can use ANDing as well as ORing, logical ANDing as well as logical ORing, to create pretty concise, specific Berkeley packet filters to hone in on the traffic that you're interested in. All of the options that are necessary to operate Snort, whether in packet sniffing, packet logging, or in IDS modes, are presented when you execute Snort with no options, such as the alert mode -A, which tells Snort to execute and to log alerts based on the item specified after, fast, full, console, etc., and many other items. Snort even has the ability to log by obfuscating the IP addresses within the packets. So you can create a modified version or a clean version or a sterile version of your logs for presentation on the internet, for processing perhaps by folks in news groups who are willing to help. In order to execute Snort in an IDS mode, however, we indicate the rules file using the c option, which indicates where the rules file is located, which has references to the different rules that are supported. You can read Berkeley packet filters from a file indicating F, and many other options, too many to go through at this particular point. So let's just jump right into sniffer mode. Snort v I ETH0 listens on ETH0. It reveals all of the traffic patterns that are occurring between the local system and remote systems. Control-C breaks the process, and if you scroll up, you'll see the various packets. Each section, delimited by the plus equal delimiters, represents a separate packet. We see the communication stream, for example, between the local system with a .10 address at a given time on a given date with accuracy that ranges, in this case, to microseconds, but can be up to nanoseconds. And we see the IP address of the local system with its 5901 TCP socket, that is. We know it's TCP, the next line tells us. And the remote system with a high port 49204 connecting to this system. And we see traffic information. This is the TCP header. So we're getting TCP as well as IP header information, or layers 3 and 4 of the OSI model. We're not seeing, however, layers 2 as well as 5 and above. So Snort VETH0 reveals layers 3 and 4 of the OSI model. We can dig in a little bit deeper using Snort, for example, VDE with the same IETH0, and you'll see the difference in the packet dump. We'll do this momentarily after we discuss some of the other options. When you break Snort in sniffing or logging or in IDS modes, it returns status information regarding the fact that it received a shutdown signal, the number of packets received, as well as the number analyzed. The number analyzed is always considered in a ratio to the number received to determine whether or not Snort is accurate, or monitoring or parsing, as well as, which means analyzing, the bulk of your packets. Because we sniffed and dumped the output to the screen, only 92 and roughly 0.5% of packets were processed or analyzed, which means roughly 4.5% were dropped. And some packets weren't processed altogether because we killed the process. There was a breakdown by protocol. This is a categorical breakdown of the process of the packets that were received during the time that Snort sniffed the traffic. One thing we glanced over but didn't mention is that when you kill Snort, it returns the number of seconds or the amount of time that it was running before it was killed. So this process was running almost 9 seconds before we killed it. And again, we see the accuracy measured in microseconds, or a millionth of a second. So here's a breakdown. You can ignore below unless you're in NIDS mode. The action stats section pertains to NIDS, how alerts are handled, whether or not items are logged, whether or not certain traffic passes the NIDS untouched. So that's a simple sniff example. But to see more detail, turn on VDE, and notice after we've just killed this process, which reveals it ran for just under 1.5 seconds, we see much more packet detail. This, for example, is a full packet which includes all of the layers of the OSI model minus the physical layer. In VDE, or when VDE is enabled, we see useful information including the TCP/IP headers that we saw earlier, which includes date and timestamp, as well as source and destination IP addresses. But now we also see source and destination MAC addresses. So this information represents layer 2 of the OSI model, whereas this information represents layer 3 of the OSI model. We also see all of the other layers up through layer 7. So we see that with the port we have layer 4 information, with the IP address we have layer 3 information, and with the MAC address we have layer 2 information. What you see here represents the packet payload, which covers layers 5, 6, and 7, or up through to the top of the OSI model. Now, if the communique between the parties is encrypted, as we see here, you'll be unable to determine or decipher what is contained within the packet stream. Nonetheless, Snort still has at least the opportunity to pick up the traffic and to attempt to make sense of it. If the packet stream is clear text, you can always reassemble it using a tool such as Wireshark. So that's what VDE turned on, which reveals more layers of the OSI model. And again, there's no need to memorize this. Just execute Snort and search for the various options in the packet output. Like we see, for example, lower D reveals the application layer, whereas E represents the second layer information. So VDE reveals layers 2 through 7, but in particular, as we saw, D reveals the application layer, whereas E reveals layer 2, or the MAC address information. So in packet sniffing mode, you can focus in on packets that are traversing the wire to and from your system and to and from other systems if you have access to those streams. Now regarding Berkeley packet filters, supposing we wanted to focus on packets destined to a given port, such as FTP or Telnet. We'll have to see if we're listening to those ports, of course. And we see we're listening to SMTP as well as SSH, or mail as well as SSH, but no Telnet. So for our intents and purposes, let's modify Zynet D Telnet. We'll set disable to no. We'll disable it momentarily after we've gotten our point across, and we'll restart Zynet D. And we can't find service because we've SU'd in, so the path wasn't maintained. Now let's netstat NTL grep23 to see whether or not it's there. Now it's listening. So a simple Berkeley packet filter would resemble the following. Snort VDE if you'd like to see the application layer as well as the data link or layer 2 of the OSI model. ETH0 and then a BPF such as TCP port 23 will reveal traffic to and from TCP port 23. This is a simple BPF. In a BPF you usually indicate the protocol type, including a specific attribute of the protocol type, such as a port, and you can include it with logical ANDs as well as logical ORs, such as TCP port 23 or port 21, or TCP port 23 and port 22 to get both Telnet and SSH. You can Google BPF or Berkeley packet filters and you'll see tons of documentation on it, or navigate to tcpdump.org, as Berkeley packet filters are supported with TCP dump, which Snort uses exclusively to log packets via live PCAP, that is. So now let's run this altered version of Snort. And now instead of seeing a load of packets traverse the screen that is, we see that Snort's waiting for traffic, but specific traffic, port 23 traffic. Let's open a separate shell, and we will SSH to a remote system. And once on that remote system, we'll then generate traffic back to our local system. That's the .10 host. Notice as soon as we made the connection, the packet dump on this screen immediately started flowing, indicating that there's a flow of packets or a flow of traffic which matches port 23. We can scroll all the way up to the top of the sequence. There hasn't been much activity, and you'll see one at a time what's transpired, including some of the clear text attributes. If you scroll down enough, you'll see what transpired between the client and the server. The connection was made at 38,400 baud. Modem speak for bits per second. And if we keep scrolling down, we'll see some clear text info. Here's the information that was returned. This is the default screen that we see back here, which includes the version of the server, its kernel, so on and so forth. And we can attempt to log in, and it just continues to populate the screen back here. And that information is broken apart or spread across multiple packets. In this case, the Linux CBT appears on 2 separate lines, but again, this can all be reconstructed. So that's a way to focus in on specific packets or a specific port, such as port 23. Let's kill this session. We no longer need it. Now to log this information, let's list usage as a packet logger. It's very simple. Just turn on the logging option using the similar Snort VDE, and if you want binary logging, which is the default, you don't even need to specify VDE. Just verbose I ETH0 with the L option to indicate where to log the file. We can make it relative to our local directory followed by TCP port 23. Let's try this out. You'll see the impact momentarily. So we'll start Snort yet again. And this will attempt to log traffic into a file relative to our current directory. We'll open a separate shell, SSH back out again to the remote system. Launch a telnet session back to the host. And then we'll kill the session by closing it, and then kill Snort with Control-C. It takes a little while. And momentarily we'll have a file which reflects the traffic that just transpired. This will be killed. The separate shell while we're waiting for it to be killed. Let's see where we actually saved our items, and there it is. It's in the Snort extract directory, and it is called snort.log with a unique timestamp, which you can expose using the Unix format that's indicated with date. The +%s format, which indicates the number of seconds since the Unix epoch. So this is Unix epoch format. So let's just note logs binary file in current directory with Unix epoch suffix. Whereas if you don't indicate a directory with the -l option, Snort will log to var log snort. That's its default directory. If it doesn't exist, it throws an error. Now, notice also that the permissions associated with this file is set to 600. Let's file Snort to see what the file program thinks about it. It shows that Linux CBT doesn't have rights to it, so over in the other shell, which we tried to kill, which should die momentarily, so we'll SU in here and just confirm the file momentarily using file snort log, and you'll see that it is a TCP dump capture file for our platform. So this file is indeed a file that's readable by any TCP dump compliant application. In addition to that, you can use Snort to read the file using the R option, just like with TCP dump. So you may read a file using R, and you may even apply Berkeley packet filters to the file so that you can parse out only the information that you're interested in. So for example, Snort read snort.log dumps the packets to the screen. And we can even apply, as we've mentioned, a Berkeley packet filter such as TCP port 21, for which we don't expect to see any traffic. And of course, if you scroll through the output, you'll see nothing matched what we searched for. Let's search for 22 SSH, nothing again. But if we search for 23, it matches all of the packets, and then they're dumped to the screen. Now, Snort is not the best application to use to reconstruct and analyze packets. Wireshark is that utility. Snort's main emphasis or excels at sniffing, logging, and NIDS. Post-processing should be performed by a separate application. So logging is just like packet sniffing, with the exception that a file is created. Now regarding that default directory, if you simply execute Snort with the B option with optional IETH0, this attempts to log in var log snort. So be sure that the directory exists. Let's try that from the shell. So it's looking for var log snort. We'll make it and then try it again. Now this creates, after we've killed the process, this has created in var log snort a file with the name, the prefix snort.log, followed by the Unix epoch date. So this is a recent entry, and if you run it multiple times, it simply creates a new file based on the latest Unix epoch date. So you're able to sort through the files. And with Unix epoch date, since it's based on the number of seconds since 1970, January 1st, simply take the numerical value that's higher to mean the most recent file. And you can also trust your OS, but in this case the OS reads 1108 in both cases, so just pick the higher numerical value for the more recent files. But you could also indicate the name of the file that you'd like to have created using the upper L option. So if you want to use a specific name, indicate upper L, and we'll create this as test.snort.log, and this will create a test.snort.log file in that same directory, still with the suffix of the Unix epoch. So as an option, snort b upper L test.snort.log eth0 creates var log snort test.snort.log.unix epic date. So in binary logging format, Snort operates much faster. We should also note that. Note, Snort drops less packets when run in binary logging mode than in verbose dump to screen mode. So when you execute Snort with the V option, that's verbose mode. That causes it to dump to the screen. And in both cases, whether as a sniffer or as a logger, Snort is indeed a sniffer. It's always a sniffer. Using the B option or the upper L option will cause Snort to log directly to a file in binary format. Dropping the V option ensures that Snort no longer dumps to the screen. That's what's important about it. We don't see the traffic flows here on the screen. And if you want, you can also turn on specific traffic to have it search for that traffic as well, to the right of course, any options that are applicable. Now next, let's set up Snort in NIDS mode. We'll create the MySQL schema and import the appropriate settings and get Snort to operate after we've applied the latest signatures from snort.org as an NIDS.